Good morning, students. In today's video, we are going to study regarding the design of cantilever beams. In the previous videos, we have studied regarding the design of singly reinforced beam, doubly reinforced beam, flanged beams. So let us continue with one problem. So we have a cantilever beam of span 3 meters. So L is equal to 3 meters we have, which carries a load of 21 kilonewton per meter, which is a factored load. So already factored load is given to us, that is 21 kilonewton per meter, that is WU. Then next is which is including self weight. So already self weight is included in this load. So again we need not add the self weight, floor finishes and all. Then next is the width of beam is 250 mm. So width of the beam, that is b is equal to 250 mm we have to design the beam, and we have to sketch the details of the reinforcement. We have to use M20 grade of concrete and Fe415 steel, that is FCK is equal to 20 and F of Y is equal to 415. So based on this data, so let us try to design a beam. So first thing is that we have to fix the dimensions of the beam, that is B and D. So B is already given to us 250 mm. Then next we'll try to fix the depth of the beam. So depth of the beam we can take it as 1 by 7th of the span, or span by 7. So span is 3000 mm divided by 7. So we will be getting 428 mm. So somewhere near to this value we can assume the overall depth of the beam. So let us assume the depth of the beam, that is equal to 500 mm, and let effective depth be 450 mm. Then next is we have the effective span, which is 3 meters. Then next is in the earlier problems we used to calculate the self weight of the beam. Then next the load which is coming. Then next is floor finishes and all we used to add. Then next we used to multiply it by factor of safety and all. But here directly they have given the load. So once again we need not do that exercise. So directly based on the given load, so let us try to calculate the moment and shear force. Compared to the previous problems what we have done in singly reinforced beam and all, if you see the way we are calculating the moment and shear, that formula is going to change. Other things, mostly the concept of designing will remain same. So if you see the moment, how to calculate the moment, that is WL square by 2. So W is 21, span is 3 square divided by 2. So if you simplify, we will get answer as 94.5 kilonewton per meter. Next is if you calculate the shear, that is WU into L, that is 21 multiplied by 3, we will get answer as 63 kilonewtons. Then next is let us check whether the limiting moment what we are getting, it is less or more than the moment which is coming on the beam. So let us check the section now. So XU by D for Fe415 steel and M20 Fe415 it is 0.48. Then next is the limiting moment MULIM is equal to 0.36 XU by D into 1 minus 0.42 XU by D into FCK BD square. So we'll try to substitute 0.36, XU max by D value is 0.48, 1 minus of 0.42 we have, XU max by D is 0.48, FCK is 20 we have, B is 250 and D is 450 square. So if you simplify, we are going to get answer as 139.68 kilonewton meter. This is the limiting moment. But actual what moment we have? 94.5 it is going to come. So 94.5 it is less than 139. So therefore MU is less than MULIM. So therefore we can design this section as a singly reinforced section. Then next is for a given moment, let us try to provide the reinforcement, or let us try to calculate the area of steel AST, that is equal to zero point 0.5 into FCK divided by F of Y into bracket of 1 minus square root of 1 minus 4.6 into MU. MU is 94.5 kilonewton meter we have. Let us try to convert it in Newton mm, that is multiplied by 10 raised to 6 divided by FCK into B into D square. multiplied by B into D. So in this formula, if you substitute, area required will be 663 mm square. 663 mm square. So now let us assume 16 dia bars. So area of one bar, if you calculate, that is pi by 4 into 16 square. So we will be getting answer as 201. So if you have 201, so requirement is 663. 663 divided by 201, if you do, nearly or approximately you'll get it as for 3 point something. That means you have to provide 4 number of bars. So therefore we will provide 4 bars of 16 dia at top. So as you know, it is a cantilever beam. The reinforcement what we have calculated, we are going to provide this as a main reinforcement, and main reinforcement is provided at the top. Then next is we'll try to calculate what you can say AST provided, that is 4 multiplied by 201. If you provide 4 bars of 16 dia, right, for 1 bar it is 201, 4 bars means multiply by 4. So area of steel provided is 804 square. Requirement was 663. So percentage of steel will be 0.714. Then next we will try to check for shear and deflection. So let us check for shear. So shear we have calculated, that is 63 kilonewton. So let us try to calculate tau v and compare it with tau c value. So tau v is equal to Vu divided by B into D. So Vu is 63 into 10 raised to 3 divided by B into D we have. So we will be getting answer as 0.56 Newton per mm square. So that has to be checked with tau c max, right? It is 2.8, so therefore it is safe, no need to redesign the section. Then next is PT, already we have calculated, that is 0.714. Then next is based on the IS code, we have to calculate the tau c value based on IS 456 table number 19. So let us so we have a 0.716 we have, and M20 we have, so therefore it is nearer to this. So if you interpolate, we are getting so value somewhat as 0.55 Newton per mm square. So as tau v is greater than tau c, tau v is how much? 0.56. It is greater than tau c, that is 0.55. Therefore we have to design this for shear. Then next is VUS is equal to tau V minus tau C into B into D. So if you calculate, we'll get answer as 1125. This much has to be resisted by the steel, shear steel what we provide. So let us assume 6 dia, that is a two-legged 6 dia. So therefore area of steel will be pi by 4 into d square multiplied by 2. Why? Because it is a two-legged stirrup. So area will be point what you can 57 square. So let us calculate the spacing, that is equal to 0.87 f of y, it is 250. ASV is 57, D is 450 divided by VUS is 1125. So steel will be 495.9 mm. Then next is spacing will be, another criteria is 0.75 D, that will be 337 mm, or we have to provide minimum 300 mm. So therefore let us provide two-legged 6 dia about 300 mm center to center. Then next is we'll check for deflection, that is L by D max has to be compared with L by D basic multiplied by KT, KC and KF, or F1, F2 and F3. These are the codes, what you can say, coefficients. So first let us try to calculate the value of this F1, that is for tension steel. Modification for tension, that is P for based on the PT, we try to calculate. PT already we have calculated, that is 0.714 percentage. So we have to calculate Fs value. So let us see the formula what we have. Already we have covered this. So once again we are checking. So Fs is equal to 0.58 f of I into area of steel required by provided. So 0.58 f of y, area of steel required, that is 663 divided by AST provided. So nearly you will get answer as 198 Newton per mm square. Then next is we have to refer from figure 4 of IS 456 2000. So this figure we have to refer, and if you compare, so PT is 0.7, somewhere here we have. So if you go somewhere here at the top, and if you find out, so nearly you will be getting it as 1. So therefore F1 will be equal to 1. The next is F2 and F3. These are for what you can say compression steel, and for flange section we don't have those cases. So therefore this will be equal to 1 and 1. So F2 and F3 will be equal to 1. Therefore L by D maximum, that is equal to L by D basic. So for a cantilever beam it is 7. Already this also we have seen. So here you can see basic span to effective depth ratio for cantilever it is 7. So therefore 7 multiplied by f1 f2 f3, that is 1. So therefore this value will be equal to 7. The next L by D actual what we have provided, that is 3000 divided by 450, it is 6.67, which is less than this 7. So therefore L by D actual it is less than L by D maximum. So therefore our section is safe in deflection, as well as our section is safe in shear also. Then next is we'll try to check for the development length. So already this LD value already we have calculated earlier one problem in the calculation of this development length. Once again let us see. So f of y into 5 divided by 4 times of tau bd, 0.87 we have. So tau bd already we have seen, this is 1.2 multiplied by 1.6, that is 1.92. So therefore LD will be equal to 0.87. F of y is 415 multiplied by 5, that is diameter of the bar, multiplied by 4 times of tau BD, that is 1.92 we have. So 47 times the diameter of the bar. Already we have seen this earlier also. Same thing we have done here also. That is 47 times the diameter of the bar. So as we are using 16 mm dia, so therefore LD will be equal to 16 times of 47. The 752 mm is the development which is required. So therefore when we are going to do the detailing, we have to show that this is the development length which has to be provided. 750 mm is the development length which has to be provided. As we have provided the reinforcement, so we have calculated this top reinforcement, that is we have calculated 4 bars of 16 mm dia. This has to be provided, and we will try to provide what you can say, as it is a singly reinforced section, we are going to provide a nominal what you can say reinforcement, that is 2 bars of 12 mm dia as the hanger bars. Then next is we have to calculate the stirrups also, that is two legged 6 mm dia about what you can say 300 mm center to center regarding this stirrups. So if you see the cross section of this, so breadth will be 250 mm, depth will be 450 mm, 4 bars at top, that is 4 bars of 16 mm dia, and at bottom we have 2 bars of 12 mm dia, and this stirrups will be two legged 6 mm about 300 mm center to center.